Now let's look at the second asymptotic notation, big O notation. Okay, so similar to the big theta notation, which bounds a function from above and below, the big O notation, we only have a upper bound. Okay, it's a bit special case. We only have the upper bound, and in those cases we use big O notation. Okay, so for a given function, now let's look at the formal definition. Okay, for a given function g of n, then the big O of g of n is also a set of functions, and the set must be satisfied in this way. So for any function in this set, there exists positive constant c. Okay, note that we only have one constant c, and n0, such that the target function is smaller than c times g of n for all the n that's greater than 0. Okay, so we only have one side. Well, on the other side, there's also a greater than 0 requirements, but only here, g of n only appears on the right side. Okay, it only serves as the upper bound. Okay, so intuitively, we can think of big O as something that's always above. Big O is always something above the target function. Okay. So when we say Fn equals, or Fn belongs to big O of g of n, then g of n is always above Fn, or as long as the n is greater than some threshold. Okay, so the f of n is always below c times g of n. Okay, so we can notice the relationship between Fn, big theta, and the big O notations, right? Because in big theta notation, Fn is like sandwiched by the upper bound and the lower bound. Then the big theta notation, it automatically implies that the big O notation also applies, right? Because big theta is a stronger notation than big O, or big theta is a subset of big O, right? So recall big theta, Fn is between C2 times g of n and C1 times g of n. So as long as this relationship is valid, then it must be true that f of n is smaller than c times g of n, right? So this is a very interesting relationship between big theta of O and big theta notation and the big O notation. So now let's look at the issue of the tightness of the bound. Okay, so after we have talked about big theta and big O, we can talk about how tight the bound is. So in the language of set theory, we say that big theta is a stronger condition. So big theta of g of n is a subset of big O of g of n. Okay, so for any quadratic function, here's an example. For any quadratic function like this, then Fn equals big theta of n squares means that Fn also belongs to the big O of the n square. Okay. So, but that's not surprisingly, that's not a surprising fact, right? We know that the generic form of the generic quadratic function can be sandwiched by two quadratic function, then it must have a quadratic function as its upper bound. But it's surprising to find that the linear function, if we draw a linear line, it also has the upper bound. It also has the quadratic function as its upper bound, right? That's true if we think about intuitively, because the quadratic function grows much faster than a linear function. Okay? But that upper bound is not a tight upper bound. It's a very loose upper bound. and the distance between the upper bound and the target function becomes bigger and bigger as n increases. Okay? So by claiming the big O notation, we're merely claiming that some constants multiple of g of n is a upper bound of fn, but we never claim that it's a tight upper bound. Okay, we never claim that it is a very tight. So by tight, we mean that by the same type of function, we can be the upper bound and the lower bound too. That's a tight bound. So big theta is a tight bound, but big O is not. So in the example here, the green line is the quadratic function, and the red line is a linear function, right? So we can find that the n squared is indeed an upper bound, but it is not tight. And one thing we want to clarify here is that in some books, some literature, the big O is used to describe a tight bound. But here, this is not the case. We will distinguish big O and big theta. And we will define the tight bound only use the big theta notations.